everyone, in the previous class we discussed about the elastic analysis of the concrete lining of a circular tunnel, and this problem was taken care by a problem in theory of elasticity of thick cylinders. And then I mentioned to you that till now we discussed about the circular tunnels only, but then in practice you have various shapes of the tunnels which may be non-circular. So today we will see that how we can determine the stress distribution around the non-circular openings in elastic ground conditions. So the method that is adopted to obtain the stress distribution is called as Greenspan method. Let us try to first understand that what are the various shapes of the tunnels that are used in the field, and then we will learn about this Greenspan methods and using which how we can obtain the stress distribution around these non-circular openings, especially in elastic ground conditions. So you take a look here. In this slide I have pasted few pictures of non-circular tunnels. So the first picture gives you the idea about the horseshoe shaped tunnel. You can see why it is called like this, because the shape of the tunnel, the cross section of the tunnel is of the shape of horseshoe. Then take a look at this figure. This looks like the shape D, so this is called as D shaped tunnel. This is egg shaped tunnel, while this one is giving you the idea that how the elliptical shaped opening will look like. Then this is the rectangular shaped tunnel. So till now what we saw was related to the circular tunnel. We saw that how we can determine the stress distribution along with the displacement along the tunnel periphery. So today we will see that how we can handle such regular shapes. So basically the shape of the cross section of the tunnel is governed by hydraulic consideration and also the stress concentration, and on the other hand the stress concentration, they are governed by the geometry of the opening. So non-circular openings analysis in elastic ground conditions was given by Greenspan in 1944, where they considered the non-circular hole in an infinite plate which is acted upon by the in-plane stresses, and these were acting theoretically at a distance of infinity from the opening. It is exactly the same as we did in case of the circular tunnels, where we considered that the applied stresses, they are acting at a large distance or maybe at an infinite distance for all practical purposes. So the exact solution for the stress distribution in such uniformly loaded plate which contains a small hole whose boundary can be expressed in the parametric form by these two expressions, which are given as x equal to p cos beta plus r cos 3 beta. Make this equation as 1a, and y as q sin beta minus r sin 3 beta, where these p, q and r, they are the parameters, and for a particular shape these are constants, and beta is the angle which is measured from x axis. So basically this is how the axes are taken. So this is what is your x axis and this is y axis, and this beta angle will be measured from the x axis. So, if we use various values of beta and the particular parameter for a shape p, q and r, then we can get, corresponding to each value of beta, we can get a set of coordinate system which is x comma y, and therefore we will be able to generate that shape of the opening. So, the shape which are given by equations 1a and 1b, they basically represent the closed curve which has symmetry about both x and y axis. So, for example, let us say if you have this as x axis and y axis, and say if we have the square type of the opening. So, basically the coordinate system is considered in such a manner that the shape is symmetrical about x axis as well as about the y axis. So, for certain values of these parameters p, q and r, the curve that will be generated by these two equations is simple and it does not cross itself. So, it is a closed curve. Now, if we adjust the values of these parameters p, q and r, we can generate variety of simple closed curves, and these include, say, circle, ellipses, approximate ovaloids, approximate rectangles with rounded corners. Now, here you see one has to take a note of this term, that is rounded corner. We do not provide this type of the corners which are sharp, but we go for this kind of rounded corners. Why? You will learn in a short while. So, here I take the notation where W naught and H naught, they are the dimensions of opening in x and y direction respectively, or we are calling W naught as the width of the opening and H naught as the height of the opening. So, in other words, we can say that W naught is the difference in the value of x when beta is equal to 0 degree and 180 degree, and H naught is the difference in the values of y when beta equal to 90 degree and 270 degree. See how. So, this is x and here it is y. This is considered to be origin, and as I mentioned that it is going to be the symmetry. So, let us say this is the shape. So, beta is measured from x direction. So, here it is 0 degree, here it is 90, this is 180 degree and here it is 270 degree. So, basically W naught is this dimension and H naught is this dimension. So, you see that if you just subtract or take the difference of the value here at beta equal to 0 and the value here at 180 degree, beta equal to 180 degree, then you will get this W naught. That geometrically also you can see from this figure. Okay. So, basically W naught will be equal to then P plus R minus P minus R. So, this we are getting by substituting the respective value of beta in our equations 1a and 1b. So, W naught you will get here as twice P plus R. Similarly, this H naught is the difference in the value of y when beta is 90 degree and beta is 270 degree. So, I will get H naught as Q plus R minus Q minus R, and then this will result into 2 times Q plus R. So, having known the values of these parameters corresponding to a particular shape, this is how we can find out the width and height of that shape of the opening. Now the question comes here that what will be the value of these parameters PQR. So as I mentioned that for a particular shape it will have one set of value. So the table here gives you the idea that for different types of opening what is going to be the parameters P, Q and R. So the first one deals with the elliptical shape of the opening. Now in case of the elliptical shape, you know that you have the major axis and the minor axis of the ellipse. So if the width to height ratio of this ellipse is 2:1, in that case P takes the value as 2, Q is 1 and R becomes equal to 0. However, in case if width to height ratio is 4:1, the corresponding value of P, Q and R becomes 4, 1 and 0 respectively. In case if you have the ovaloidal shape, then again for two different ratio of width to height, you have the values which are given by these two rows. In case you have the square shape opening with rounded corners, so in that case height and width ratio is going to be equal to 1 and the value of P will be 1, Q will be 1 and R will be minus 0.14. Now here the condition is that side should be parallel to coordinate axis. This means that if this is the coordinate axis, so the sides should be parallel. This should be parallel to x axis and this side should be parallel to y axis. You can have another combination which can be something like this. So this is x and this is y, where you have the diagonals. You see diagonals parallel to these axes. Okay. So here you have these two diagonals which are parallel to or maybe coinciding with the x and y axis. So these are the constant for this condition. And that is why we are writing side parallel to the coordinate axis. Then the generalized expression for the tangential stress irrespective of the shape of the opening, this was derived by these research workers and it was seen that this is the function of these parameters PQR, angle beta and the stresses Sx, Sy and Txy. So Sx and Sy, they are the normal stresses in x and y direction respectively. So this is again a complicated and long expression in terms of these quantities, and we are making this equation as equation number 2. Please note that you don't need to remember this expression because usually you know that the various parameters like PQR, they are given to us, and then to be specific we do not talk in terms of the most general state of stress. So we consider some particular state of stress, and for those situations you get a very simple expression for the tangential stress. So you don't need to bother about remembering this long expression. This is only for your information that such things exist. Now these equation 2, as I mentioned that for any shape of the opening which is represented by equation number 1, we can use equation 2 to calculate the tangential stress for any applied stress field. However, it is more instructive to consider basically 3 simple applied stress field. What are those? Let us take a look. So, first we define case 1. Here you have Sx not equal to 0, but Sy and Txy is equal to 0. So, in this case, if you substitute these values in the previous expression which was given by equation 2, what you are going to get is sigma T upon Sx will be equal to d sine square beta plus E upon A sine square beta plus B cos square 2 beta plus C. So, this is equation number 3. Similarly, we have the other two cases such as case 2 where you have Sy not equal to 0 and Sx and Txy they are equal to 0. So, what we get here is sigma T upon Sy as f sine square beta plus G upon A sine square beta plus B cos square 2 beta plus C. So, this is what is going to be the resulting expression in case if you have this type of state of stress. And then finally, the third case which I represent as case 3. In this case, Txy is not equal to 0, but Sx and Sy both are equal to 0. So, accordingly, what we have is sigma T upon Txy, this is equal to H sine 2 beta divided by A sine square beta plus B cos square 2 beta plus C. This is equation number 5. So, these constants A, B and so on up to H, these are the functions of P, Q and R. So, let us take a look that how these are expressed in terms of P, Q and R. So, here we have A as P minus Q into P plus Q minus 6R. Then I have B as minus 6R P plus Q. We have C as Q square plus 6RP plus 9R square. Then we have D as P plus Q into P minus Q plus 2Q into P plus Q minus 6R divided by P plus Q minus 2R. And E is expressed as Q minus 3R. Here we have Q plus 3R minus 2Q P plus Q divided by P plus Q minus 2R. F is given as P plus Q in bracket P minus Q minus 2P into P plus Q minus 6R divided by P plus Q minus 2R. Then G is equal to Q minus 3R this is Q plus 3R plus 2P P plus Q upon P plus Q minus 2R. H will be equal to P plus Q whole square, that's P plus Q plus 6R divided by P plus Q plus 2R. So, this is how all these constants or parameters A to H they are obtained. So, basically here the stress concentration factor is the function of geometric parameters only, and it is not the function of material properties. See, it was all the function of A, B, C, D to H, and you can see that these are all the functions of P, Q and R only, which depends only on the geometric parameters and not on the material properties. So, what happens in case if you have the elastic stress distribution? In case of such situation, superposition principle holds good. So, in case if you have the biaxial state of stress, then in that case stress concentration factors they can be obtained directly by adding two uniaxial state of stress situation. Like previously we saw that case 1, case 2 and case 3, all the three were uniaxial state of stress. Now, in case of the situation that Sx and Sy both are present and Txy equal to 0, then you can apply the principle of superposition and can obtain the stress concentration factor. So, let us take a look that if we consider the biaxial state of stress, so accordingly we define the fourth case here, where you have Sx not equal to 0, Sy not equal to 0, but Txy is equal to 0. That means that the stresses are applied in x as well as in y direction. So, in that case you sum the expression for sigma t in case of when it was uniaxial state of stress with Sx equal to 0 and when it was for Sy equal to 0. So, ultimately what you get here as sigma t equal to dsx plus fsy into sine square beta plus Esx plus Gsy divided by A sine square beta plus B cos square 2 beta plus C. So, this is nothing different than what we did in case of the uniaxial state of stress with reference to case 1, 2 or 3. So, when you have the presence of Sx as well as Sy, simply you have to do is find out sigma t as if it is only Sx which is present, find out sigma t as if only Sy is present, then sum these two and you will be able to get the tangential stress in case of the biaxial state of stress. But please note that this superposition principle holds good when we have this elastic stress distribution. If it is not so, then we will not be able to do such a simple superposition. Now, the constants which are there for calculation of the boundary stresses by this Greenspan's method for various types of opening. So, here you see that for 2:1 ellipse. So, when I say 2:1 ellipse means W naught upon H naught equal to 2:1 and the shape is elliptical. So in that case what we have as P as 2 Q1 R equal to 0 and the constants A to H, they are given in respective columns. For example, for the first case, that is 2:1 ellipse, A is 3, B is 0, C is 1, D is 9, E is -1, F is -9, G is 5 and H is 9. So likewise, if you have different shapes such as ovaloid, again with two ratios of W naught upon H naught, then the square shape, of course you need to have here the rounded corners, and there two situation can be there, as I already explained you. In first situation the sides are parallel to the coordinate axis, and in another situation the diagonals are parallel to the coordinate axis. So you see that in both the cases, although it is the square opening in both the cases, but then the constants are different. Although P, Q and R parameters are same, but you see here the value of C is different, D, E, F, G and H, they are all different for these two situations. Now based upon this, for various cases, as we considered, and I explained to you that the case 1 corresponds to when you have the uniaxial state of stress with the stress in x direction only, and there is no stress in the y direction, and Txy is also equal to 0. So in that case the stress concentration factor is given by sigma T upon Sx. If you have the second case, then in that case Sy is non-zero and the remaining two stresses are equal to 0, and the stress concentration factor is defined by sigma T upon Sy. And in case you have the third situation, there Txy is non-zero and Sx and Sy both are 0, and therefore the stress concentration factor is defined by sigma T upon Txy. So these three curves are there in each of the figure for different shapes of the opening where these cases are defined. For example, here we are dealing with the elliptical opening. So the stress distribution around that periphery of this ellipse, so that is from here it starts with 0 degree and then it goes up to here as 90 degrees. So this curve corresponds to this first condition. This is for the second condition and this is for the third condition. So likewise similar way we are going to discuss the boundary stress for different types of openings. So here the first figure deals with the ratio W naught by H naught to be equal to 2, and then you can see that at the boundary here at beta equal to 0, how this stress concentration is -1, and at beta equal to 90 it is 2. For example, in case of the second case, that is this one, when you have the stress applied in the direction of the y axis, then in that case at beta equal to 0, you will have the stress concentration factor as 5, and for beta equal to 90, you have the stress concentration factor as -1. Similarly, for the third case also the variation can be seen in this manner for various values of beta all along the boundary of the opening. So similar is the situation here, but then you can see that there is a difference in the magnitude of the stress concentration factor. For example, just take the same stress state, that is, let us say state 1, case 1 I consider. So beta equal to 0, it is -1 here and -1 here. but see beta equal to 90, it is somewhat approximately say 1.5 here, and here it is 2. So when W naught upon H naught is increased from 2 to 4, you see that the stress concentration factor at beta equal to 90, it reduces from 2 to 1.5. And similar type of comparison you can make for all the respective cases. For example, let us take case 2 here. See beta equal to 0 and stress concentration factor you get as high as 9, while it was 5 in this case. Although at beta equal to 90 you have the same stress concentration factor, that is -1. So this was about the elliptical opening. Now in case if you have the ovaloidal shape of the opening, so we write here as approximate ovaloid because of the fact that those equations 1a and 1b, if you just substitute the particular values of p, q and r, you can only generate the approximate ovaloid. So that is why we are calling here as approximate ovaloid, but it is as good as ovaloid for all practical purposes. So similar type of comparison and the distribution can be seen in these two figures, which typically represent the stress distribution all along the boundary of the ovaloidal shape of the opening for two situations for width to height ratio as 2 and 4. So again in this case here all the three cases have been shown. Again the three cases, they correspond to these state of stress. So if you just compare these two, probably let us take the case 3. So you see the maximum stress concentration factor is somewhat here, which is maybe larger than 6. However, in this case you see it is little larger than 5. So the pattern may be the same, but the magnitude is not. It depends upon the size of the opening. Similar observations are made here with reference to the square opening with rounded corners, and since it is the square opening, so you have W naught upon H naught to be equal to 1. So be careful here that this is what is for situation 1. This is for state of stress designated as case 2, and this one is for case 3. Similar is the situation here. So the difference between the two situation is, in this case the sides are parallel to axis, you see here, but in this case diagonals are parallel to the axis. So this is the diagonal which is maybe merging here with y axis, and this is another half diagonal which is merging with x axis. So based upon how the shape is placed, accordingly you will have the different stress distribution. Please note that here we are only talking about the boundary stress distribution. Now if you just take a look, the magnitude of the stresses or the stress concentration factor is larger here in this case as compared to when you have the sides which are parallel to the axes. So here as I have been mentioning that we do not have the sharp corners. For example, let us say if I have here this type of situation, very sharp corner. So this situation is avoided. The reason being that the stress concentration factor at such sharp corners becomes infinite, and it is impossible that any material can withstand that kind of infinite stresses or huge stresses. That is why, to do away with such type of situation, the corners of the opening, they are made little rounded like this. This is what is needed, not this. This is not correct. This type of sharp corners, they are not used, not adopted. So, if we take a look at these figures, close look corresponding to any particular shape but different aspect ratio, or if you compare two different shapes with the same aspect ratio, for example, if you compare 2:1 ellipse with 2:1 ovaloid, then by studying these distribution for the boundary stresses for different shapes of the openings, then we can come out with some general guideline for the design of these openings. So, this we will discuss in detail in the next class. So, what we discussed today was that what is the Greenspan method, how it helps us in obtaining the stress distribution around the non-circular openings such as elliptical, square or rectangular opening, and how for different shapes you can get the boundary stress distribution and how they compare with each other. So, we will deduce the general guideline for the design of such underground excavations in the next class. Thank you very much.